All right. So just a continuation of electricity and magnetism now. Okay. So now we're going to start talking about electric current, right? Electric current. Uh, there's two types of electric currents. There's DC, right? And there's also AC. Okay. And in DC current, electron flow is always in one direction, from negative to positive. Okay. That's literally what you see in batteries and you see in automobiles, right? They're all going in one direction with their electricity, okay, with the flow of current. And so that's why when you look at a battery, you see one side is the positive side and one side is the negative side, and you have to put the battery into whatever you're putting it into correctly, or you won't be able to get anything out of it, right? So that's the thing about direct current. Contrast that with alternating current, right? It's constantly changing from the voltage from positive to negative and back again, right? And it's exactly what it sounds, right? It's like, and we'll take a look at a picture of it in a second, but it's literally a rotating generator inside of an electric field, right? And that motion right there turns makes the flow of electricity occur, and that's why you get electricity. And so while batteries are being used in homes, I mean, sorry, and batteries are being used in automobiles and boats and all that stuff. Uh, in your homes, in our homes we use alternating current, right? In our homes we use alternating current, and specifically we use 60 hertz at a voltage of either 110 or 120 volts, right? 110 or 120 volts, right? That's like all the normal appliances that you use, like your fridge, your microwave, your TV, um, your Xbox, your Switch, all those things run at 120. But some of you know that if you have like a dryer in your house, it has a much larger plug in it, and that dryer runs at 240, right? So, because it requires more current to actually run a dryer because the dryer gets super hot. So yeah, but while most of the house electricity coming in is at 120 volts, you do have some plugs, like in your garage for your hot water heater, or in your laundry room for your dryer. They do run at 240 volts, right? They do run at 240 volts. So let's talk about a simple electric current, right? And you've seen this already before because we did a lab on it a couple weeks ago, which I thought was pretty fun because I added as many batteries as possible to make the light bulb explode, and it was different. It was different number of batteries each time. One time it was like 4 batteries. One time it was 3 batteries. By explode, I just mean it burnt out the bulb, which is going to be a bad thing for next semester's class since they don't have as many bulbs anymore. I hope they don't make me replace those. Anyway, plugging appliances into wall outlets places them in a circuit, which is either in series or in parallel. Okay, the series circuit, in the series circuit, the same current passes through all the resistances. The total resistance is simply the sum of the individual resistances, right? And we'll look at a picture of that in just a second. So if you remember back to your lab, the something being in series, right? Whether it be batteries or it be light bulbs or whatever, literally in series just means one comes right after the other, right, inside the circuit. So here's a quick picture, right, of what it looks like to have a circuit that's in series, right? If one bulb were to burn out, the circuit would be broken, and then all the lights would go out, right? What's a good example of that? Exactly. Christmas lights. I'm actually putting up Halloween lights right now at my house, and same problem because they're just orange and purple instead of all the Christmas colors. But Christmas lights are the exact same way. You have one bulb out of like 200. Just one of them goes out, you break the circuit, and you got to go through and figure out each bulb which one's the one that's not working. And so when you have more than one battery, which is what I did to try to blow up a light bulb, right? You're actually adding in more current. Whereas when you're adding in more light bulbs, that's adding in more resistance, right? That's adding in more resistance. And so the reason why that's adding in more resistance is because the electricity has to flow through the light bulb. There's a tiny little filament right there, tungsten, I believe. It's a piece of tungsten. I think that's what. I keep on saying Alexander Graham Bell, but no, it's Thomas Edison. Thomas Edison, found a thousand ways not to make a light bulb, but then he found the one thing that did work, which was a tungsten light bulb. a very thin piece of metal tungsten that when you run electricity through it, it glows, right? It glows for a pretty long time until it burns out, of course. And so the reason why it glows like that, and the reason why it gets so hot, well, first of all, it's glowing because it's getting hot, right? That's the first thing. And the reason why it's getting so hot is because tungsten doesn't conduct electricity uh, as well as the metal copper wire that you use to connect the batteries, and so that's why that adds resistance to the circuit. So how do you calculate the resistance in a circuit? Quite simply, the total amount of resistance is just the sum of all the resistances together, right? The sum of all the resistances together. Quite simple, quite simple. The series circuit is quite simple, right? So this is this might be an important statement since it's all here by itself, right? In a parallel circuit, the voltage across each resistance is the same, but the current through each may vary, right? The current through each may vary. Okay. So let's talk about the parallel circuit now, right? We have the parallel circuit, and a lot of you tried to do this when you did your lab. In the parallel circuit, right? I don't know if you noticed this, but like for example, uh, the series circuit, right? You quite literally you're going like positive to negative, positive to negative, positive to negative, positive to negative, right? And then back to negative again. And so if you put a battery in there, you always put the positive over here and the negative over here. It's kind of like you have to put the batteries all in the same direction inside of the remote, you know? They have to all go in the same direction. It's not that way when you do it in parallel, because in parallel, right, it's almost like you have a battery and then you have a big wire, right? You have one wire right here, and then that has a light bulb, but then you connect it to another wire, right? And then you connect to another wire. And it doesn't have to necessarily be positive to negative like it is in series, right? In fact, this is the positive side over here connected to this positive side, right? And this is the positive side over here connected to this positive side, and all these sides are the negative sides, right? So the big difference between the parallel circuit and the series circuit is that in the series circuit, you have to go negative to positive, right? Or positive to negative. You have to go all in the same direction. Whereas here, we have all the positives on one side over here and all the negatives on one side over here. They don't have to be flowing in the same direction. Does that make sense? Right? Doesn't have to be, right? So here, right, the same thing again, except this time, the same thing again. Currents divide. The current divides. The voltage is the same, right? Is what I was saying before, right? And the total current, which is I, right? Current is I, isn't it? I think so. The total current is again the sum of all the currents gives you the total current. Okay. But this time the resistance, right, is actually 1 over the resistance. So the 1 over, it's the sum of everything. Excuse me, one more time. The total resistance is really 1 over each of the resistance summed up, and that still equals 1 over the resistance, the total resistance, and you can just figure out what that is with some math. But I won't ask you to do that. I won't ask you to do that. The only reason why I wanted to show this is that you see how this here has 1 over the R, right? Whereas over here, it was just R. Does that make sense? Right? You can just add them up and you'll get the total resistance. But over here, for the parallel, you actually have to add up the reciprocals, right? You have to add up the reciprocals and then solve for the parallel resistance, okay? So in this very quick example here, right? In this very quick example here, you say you had 3 resistors, right? One of them had a resistance of 60 watts. One of them had 6 watts. The second one has resistance of 6 watts. Uh, sorry, what the heck's happening here? 6 resistance of 6 watts. That must be a typo. That must be a typo. Ohm should be the resistance. Should be the resistance unit. Anyway, so 6 ohms, and then 3 ohms, right? What is their total resistance when connected in parallel, and how much current will be drawn from the 12-volt battery if it's connected to the circuit? 12-volt battery is like a car battery, right? So again, all you do is, the total resistance here, 1 over RP, for parallel is equal to the 1 over RPs of all these added together, right? So 1/6 plus 1/6 plus 1/6, right? What does that equal? That equals 4 sixes, right? 4 6, 4 sixes, which all you have to do is find the common denominator there, right? Which is 6, and you make that 2 there, so it's 2 6, and that's why it's 4 6, right? And then if you have 4 and 6, you can solve for the RP, and now you have a total resistance of 1.5. And then you can just use our current VIRP, current equals V over RP to get your total current drawn, right? So I'm not going to ask you to do this calculation at all, but I just want you to see how it's a little bit more difficult to figure out what the total resistance is when you have it in parallel, right? It's a little bit more difficult. So one question I might ask you on an exam would be, I would show you a picture of a circuit, right? And I would ask you to figure out its total resistance, right? Which would you do? Would you do this one right here, right? Or would you do the one where you just add it up all easily, without the reciprocals? That's the kind of question I might ask you. All right, so taking a look at household circuits, right? Taking a look at household circuits wired in parallel, right? Independent branches of any particular circuit element can be operated when others have the same circuit do not, right? So in your house, most of your houses are actually wired in parallel, which makes kind of sense because have you ever had this thing happen where you put too many things on one plug and it just blows out everything in that breaker? You got to go reset the breaker, but it doesn't blow out everything in your whole house, right? So like the front part of your house doesn't have any power, but the rest of your house still has power. That's because each circuit is on a parallel, right? And so whatever happens, you still have part of it connected to electricity, right? Whereas that one section of the parallel circuit might not have electricity because blew out your oven or something because you're baking too much, right? It happens the most when you have things that are heating. Like if you have like an oven connected to the same circuit as you have a space heater, as you have a hot water heater, all those things, because generating heat is actually super difficult to do. That takes a lot of energy, as evident by your electricity bill during the wintertime, right? And so if you have all those things on the same circuit, it's a lot easier to blow those parallel circuits. But the good thing is, since they are on parallel, right? Say you have, this parallel circuit right here, and you've got like 20 things connected to it, like a hair blow dryer, your phone's charging, your computer, your light bulb, all this stuff, and it blows that circuit. This part right here won't go out, will go out, right? But the rest of it still works, right? The rest of it still works. And then, as I was saying before, your bigger appliances that require a lot of heat, like your ovens and your hot water heaters and your dryers, right? Your clothes dryers, they all run on 240, right? They all run on 240 volts. When the vast majority of all your home appliances run at 120 volts. Okay. First question. Forgot to put the A, B, C, and D again. Dang it. First question. What is the voltage used for large appliances in American households? They've been really harassing me about me doing my attendance, so please sign in and do me a solid and sign in, so I'll have your attendance for today. Do me a solid. So I just said this. Our large appliances, right? Our large appliances do what voltage? Let's see how many people were listening to me this time around. Show more. Magnets, no. Braking distance. Oh my God, what am I doing here? Light speed? What's going on here? Ah, here it goes. That's not the one. What the heck? Why is it always so hard for me to find like our stuff in here? It's just, it really kills me sometimes. Ah, here we go. Finally. Jesus. All right. So, voltage, I believe, is the one, right? I got 23 responses. That's almost everybody in here. Wonderful. And then let's hear. Oh, good, good. The vast majority of you got that one correct. The answer is indeed C, which is 240 volts, right? 240 volts. Good job. Good job. Oh, my favorite is next. Electrical safety. uh, anyway, wires become hot as more and more current is used on numerous appliances. Fuses are placed in the circuit to prevent wires from becoming too hot and catching fire, which that happens a lot at my house. I'm just kidding. No, I have a lot of a lot of extension cords, especially during the holidays, just going all over the place, right? So the fuse is a filament that's designed to melt and thereby break the electrical circuit when the thing gets too hot, right? So have you ever looked at a fuse before? It's like a tiny piece of plastic, right? And then inside this looks like a little wire, right? Tiny inside, and that that fuse actually, like it says on there, has a tiny little piece of metal in it, right? That actually melts when it gets too hot, right? I don't remember what metal is in there, right? It's definitely not like a tungsten because tungsten is in your light bulbs and it works fine, right? But there's a metal in there that actually melts, right? And so so a lot of people always think that what's happening when you blow a fuse, it sounds like you've got too much electricity going in there and it's like exploded, right? It's blew it kind of thing, like a kind of blowing a light bulb type of thing. But in fact, what's happening is that metal is actually melting, right? And when it melts, that's when you break the circuit. That's why you got to replace the fuse, right? So, I mean, even I used to think that when you blew a fuse, you actually blew something, right? There was like too much electricity and something blew and sparks and stuff like that. No, no sparks at all here. The metal inside the fuse is actually melting, so it breaks the circuit and you can't use it anymore. You got to replace it, right? And that forces you to have to pull the fuse out, let the wire cool down, and then plug it back in again, right? Or remove some of the appliances you have attached to it. Does that make sense? Right? So there are two types of fuses. There's the Edison type, and then there's the S type. Circuit breakers are generally now used, right? Circuit breakers are generally now used. Um, and I can't remember. I had back in my old house. I used to have these fuses that were like circular, that were really weird. But now everybody uses circuit breakers. Okay. Oh, this is fun. This is fun here. Electrical safety with a dedicated ground. This man looks like he's getting electrocuted right now. I think that's him getting electrocuted. A dangerous shock can occur if an internal hot wire comes in contact with the metal casing of the tool. The danger can be minimized by grounding the case with a dedicated wire through through the third wire plug on the third wire on the plug. Right. So have you ever noticed how some plugs have two prongs and some plugs have three prongs? I was about to say one prong. You have a problem if you have a plug with one prong. But but so you have the two, which is positive and negative, right, to plug into the wall, and then some of them have the grounding one too, which is the third round one at the bottom. So there's a three plug, and those are always safest to use. And the reason why is because the funny thing about it is that the picture of this drill this man has here is a very old style drill, and most of these drills only have those two prong plugs. So it's actually very likely that you get electrocuted using one of those drills, right? So, but most power tools now don't have that. Most power tools have the three prongs, and so uh, the thing is, like, what happens is that if you're holding the drill and you're drilling into the wall and then a wire inside say melts all the plastic because it got too hot and touches the metal case of the drill and you're holding the drill, the only path for the electricity to go to get to the ground is you, right? So the electricity will go through the drill, hit your hand and go through your body and go to the ground, right? It's just like it's just like lightning. Lightning always comes to the ground, right? It doesn't go up to the sky. It always wants to come to the ground. So if you have that third prong, right, there's an easier path now for electricity to travel, right? Because it turns out that when you get electrocuted and go through this way, there's a lot of insulation happening there, right? Your body's insulated, your skin's insulating, but it's still a path to the ground. But if you put in that third prong, now there's a grounding wire, which is an actual piece of metal, right? It's actually a piece of metal, a wire that connects any kind of electricity inside of the drill straight to the ground. And so the electricity would much rather go through the grounding wire, right, to get to the ground, than go through you to get to the ground. Does that make sense? And that's why having that third prong is safer, right? You won't get electrocuted because you won't get electrocuted because the electricity from that hot wire would rather come down here using the metal wire called the grounding wire than going through you, right? So there's a lot of confusion, right? Because when you look at like electricity, you always see the red side and you see the black side. And the black side people always think is ground, which is it sort of is ground, right? But really, it's where the negative terminal is, right? So you have electricity going in the circuit, and positive is always red, and negative is always black. And so the electricity is going around in the circle, and it's coming out. Oh, sorry, it's coming out of the black side and going to the red side and going around in this circle. So none of that actually is grounded, right? It's actually there's a closed circuit, but nothing is touching the ground, and so uh, when you add a third wire to the system and have it actually touching the ground, that's how you prevent yourself from getting electrocuted and stuff. So your cars do that too. Have you ever seen it where if you pop the hood, you have the car battery inside and it's attached to your alternator, right? The red side and the black side's connected to your alternator, which recharges your battery while you're driving, right? But then there's also a black wire that's connected to all your electronics and then connected to the frame of the car, right? It's grounded to the frame of the car. Because that way, while you're working inside the car, right, you don't get electrocuted because the electricity will go through the ground, through the car to the ground instead of going through you to the ground. Does that make sense? Right? So we always think of circuits as being these two wires that are connected together in this big circle, but you can also have a third one coming off and have it come to the ground. Oh, this is what I was talking about before. So back in the day, back when I was living in Auburn, I actually had a house that was like built in the 50s or the 60s, and instead of having a breaker box, when we blew a breaker or whatever like that, and you go to the breaker box in your garage or whatever, and you switch those things back and forth, those little they'll be red if you had a problem, they'll be red. So you'll reset it by turning it back to black and to red and black again, and then you can reset your breaker that way. But in the olden days, right? In the olden days, they actually had this kind of fuse where you couldn't just switch it back and forth. You actually had to go buy more of these fuses if you had blown one, right? It wasn't just as easy as switching your switching your breaker box back and forth. And the funny thing about this is that you can barely find these anywhere now because houses don't get made with these anymore. So you got to go on Amazon and buy like a pack of 50 instead of being able to like just go to Home Depot and get one, to do your thing. So older houses have this, right? Have this thing, and this is the fuse right here, right? That's the fuse. The circuit goes in there, right? And what happens is if you've got your hair blow dryer, your curling iron, your space heater, your heated blanket, and your Nintendo Switch all attached to this one circuit, it's definitely going to melt that down, right? And you won't be able to have any more electricity in your house, or at least that part of the house. So you have to replace these things, okay? So this is another type of fuse too. This is an Edison base, and then this is a Type S. Very similar thing. If you didn't know this, the color of the fuse actually denotes what the amperage is, right? So I can't remember what the amperage is in my house. My old house, I'd actually used these things, but they were orange. So I'm pretty sure that was like maybe 30 amp fuses. Orange was 30 amp fuses. No, not 30. Sorry, 40 amp fuses. 30 is green, 15 is blue. It's not like anything you really care about unless you live in an old. If you live in an old house, then you care about it. But if you don't live in an old house, you're fortunate enough to have a breaker box, right? A breaker box. All right, so thermal type circuit breaker. So this is how most modern houses work now, right? They don't use fuses anymore. They use breaker boxes, okay? And so this is called the thermal type circuit breaker, or also known as a breaker box, right? As the current through the bimetallic strip increases, it becomes warmer, right? The Joule heat, right? And it bends. And when it bends, it trips the circuit breaker, right? Isn't that cool? Isn't that neat? So here's your here's your normal, circuit, you're doing fine in your normal circuit right there, right? And this is the switch right here, right? This is a switch that you pull back and forth, okay? And so what happens is that, say again, again, you're like you got your switch and your computer and your fan because the room you're in is hot, the speakers, the TV, and then an air fryer, right? All those things. All I don't know why you'd have an air fryer in your game room, but have an air fryer in there, making your pizza rolls or something for the next gaming session you have, and it's all coming on into this current right here. And what happens is that this metal here, right, when it gets hot, it starts to bend. What does that remind you of? It should remind you of something that I asked you about on the last test. Yes, the thermal expansion of brass and iron, right? The thermal expansion of brass and iron. And so when you have those, the reason why it's bimetallic, right, is one of those metals has a larger thermal expansion than the other metal. So when it warms up, it bends. It doesn't just extend and get longer, but it actually bends. And it has to do that, right? Because if it didn't do that, I mean, nothing would really happen. And so yeah, see, if it extends, it just gets longer. It doesn't actually, do anything. But the thing is, right, if you have all those things, including your air fryer in there, it gets really hot, the thermal expansion of one of these things is probably this one right here, the one that's on the left side, is larger, so it gets to expand a lot more. And when it does that, it bends. And when it bends, it pushes this little L-shaped thing here, right, the latch. And when it pushes the L-shaped latch, this little spring right here releases, and then you release your circuit breaker. And that's why you lose power in part of your house, right? And so what do you do then when you want to restore power to that part of the house, right? Well, first thing, have you ever tried to reset your circuit breaker and it doesn't work? Right? It doesn't actually return power to the house. And you're like, what the heck's happening? The reason why that is because this is probably still bent, right? And you need to let it cool down first, right? So that's the first thing. Then after a while, you do it and it works fine, right? And so literally all you're doing when you're doing that little back and forth in your circuit box, in your breaker box, is you're just pushing this thing forward and backwards again, right? To put it back into position so that it pushes this guy up, and then you close the circuit again. Does that make sense? Right? So the next time you blow a breaker at your house and you have to go reset it, you know exactly what's happening. You can tell somebody, hey, this is what happened. Did you know that there's a bimetal piece of metal in there that bends, that does that? That's based on thermal expansion, right? So this is actually pretty interesting the way this works, right? I mean, whoever came up with this, way better situation than having fuses, let me tell you, right? Way better situation than having fuses. Uh, and then uh, I don't know if you guys in your houses have this, but in my house we have this one switch that's at the bottom, and it's at the bottom of the circuit box, and it says on and off main power, right? And so it's the same thing with that, except it's huge, and you can shut that thing off and shut off power in the entire house, right? I mean, I would never do that, kill my animals or something, but it's kind of cool to have that option. Okay, so your next question is this: which of the following is true about electrical safety? Which I don't even know, so I need to read this. I challenge you all to go home today and play with your circuit breakers. You know, Like like I said, put on an air fryer and a curling iron and an iron and a blow dryer and a space heater all in one plug, right? Just one plug. That should blow your circuit breaker, right? And then immediately run to your circuit breaker and try to flip it, right? And see if it works. And if it doesn't work, wait like 10 minutes and then do it again and then it'll work. I challenge you to do that. It'll be a good time. And when it does that, right? When it happens, right? Like I mean, I don't know if you live with your parents or maybe whoever your roommate or whoever you're living with. You'd be like, "Oh, I know how that works. You just have to wait like 10 minutes, and then it'll work." And then you show them how much you know. It's good. It's like it's a party thing. It's a conversation starter. Did you know that this is how? Okay, I don't even know what the choices are. What are the choices? Wires can become hot as more and more. That's true. Fuses are placed in the circuit to prevent wires from becoming too hot and catching fire. That's true. The fuse filament is designed to melt when the current. So all these are true. All these are true. And yes, you all chose true. Thank God for that. I don't want any burned houses, right? I don't want any burned down houses. So good times, good times. All right, so that takes us over to magnetism. That takes us over to magnetism. So magnetism is closely associated with with electricity, right? In fact, electromagnetic waves consist of both vibrating electric and magnetic fields, and this phenomena are basically inseparable. You can't separate them, right? But back to Earth. Let's bring it all back to Earth for a second, right here, right? A bar magnet has two regions of magnetic strength, and they're called poles. One pole is called the North Pole, and one called South Pole. Right? One is called the North Pole, and one is called the South Pole. And everybody should know this. I'm sure you've played with magnets before. If at all you bought some magnets when you went on vacation and put it onto your refrigerator, right? A lot of people collect refrigerator magnets from all over the country or all over the world, right? I'm sure you can get like a Texas Wesleyan magnet, right, to put on your wall if you're so inclined to support your school that way. So many of you are wearing Texas Wesleyan things, right? Speaking of wearing, representing, I don't know if you heard last week, Dallas County lost like 17,000 criminal cases. I'm glad I don't work there anymore. So, yeah, apparently there was some kind of like error in the IT department or something. Someone made an error and they accidentally deleted 17,000 criminal cases. Ooh, that is rough. Huh? I believe I believe they said it was just a mistake. Someone made a mistake and accidentally deleted like all the files for 17,000 different criminal cases. So all I'm saying is thank God I don't work there anymore because I would be having to help deal with that stuff. But that is true though. It is scary because many of those cases are going to trial and they're not going to be able to go to trial if all the evidence is gone, right? So yeah, I'm glad I'm not working there anymore because it is a cluster F. I don't want to say the word, but cluster F over there right now. Okay. Right. So I don't know what that had to do with magnets. What does that have to do with magnets? Oh, I remember what it was. I said something about Wesleyan magnets, and then you were representing Texas Wesleyan because you were wearing a lot of Texas Wesleyan clothing, and then I said I was wearing a Dallas County thing because I was representing them, but then I'm glad I'm not working there anymore because of the cluster F that's happening over there right now. There we go. See, look at that. That was like 5 degrees of separation. It's great. Good times. Right? What is the other game you play? Like 5 degrees, 6 degrees from Kevin Bacon or something? Right? Ever heard of that one? It's good times. It's good times. Anyway, so let's talk about the magnetic poles for a second, right? So the North Pole of the magnet is called the North Pole because it seeks north, right? It points to north. The South Pole of the magnet is south seeking, so it points south. So that's pretty obvious. Magnets also have repulsive forces too, so specific to their poles. This is called the law of poles. I feel like we talk about a lot of laws here, right? Like poles repel and unlike poles attract. So north and south attract, and south and north repel each other, right? That's pretty obvious. Okay. So this is your next question. Which of the following is not a pole of a magnet? I swear if any of you get this one wrong. I say that, then like half of you will just on purpose get it wrong. Okay, well, one person picked D. Like seriously. I mean, surely they're just kidding. Whoever this one, do I need to look up to see who this one person is? Like seriously, right? Are you punking me? Who's punking me? Like, I have to know. I'm gonna see who this person is. I won't say it out loud because it's like a FERPA thing or something. But I'm gonna have to see who this person is that picked D. This is unbelievable, unbelievable. Oh, that is so funny. It says, "Please be aware of your students' privacy." Oh, I knew that the person did that because they've been doing it this whole time. All right, next question. All right, so the law of poles. Okay, the law of poles. Um, so like poles, right, repel, and then unlike poles attract. So if you point the north end of a magnet to the north side of a magnet, it's going to make the magnet, if it's on a string, turn away from it, right? But it's also going to make the south side of the magnet turn towards the magnet that's in your hand, right? And the same is then true of the other side too. If you put a south side on the attracted to the, it's going to be attracted to the north, pulling the north towards the south, and then pushing the south away from it. So in both cases, if you do this, you can actually make a magnet spin around in circles like indefinitely. It's actually kind of fun, right? It's kind of fun. But then on the other hand, though, right? On the other hand, uh, since unlike poles attract, the only thing that's going to happen here is the North Pole will just attract to the South Pole, and that's it. So there we go. All magnets have two poles, and they are dipoles. So di means two, right? And pole means two poles, and I'm sure this is just two So there's, I got you, I got you. Um, hmm. These are repelling each other here, and these are repelling each other. Why would they not put two of them that are attracting each other? That makes no sense. Stupid picture. I'll come up with a better picture than that for your exam. Okay, like the one with the dog falling. Right? How many of you got that one question right with the dog falling? That's the answer to that question was that the dog is coming towards the ground at the same rate that that the ground is coming towards the dog, right? Right. So, and then the other dog question was what is true about the force of the two dogs that were playing tug of war? And sadly, I think that was that a pit bull. I can't remember. I can't remember what the other dog was, but it was dragging that German Shepherd across the ground because you saw the little drag marks on the sand, right? So clearly that means that the forces were unequal that time, right? So you didn't see the drag marks? It- yeah, I mean the drag marks. Come on, the drag marks. There were drag marks in the sand. Yeah, crazy, killing me here. You can expect more dog pictures to represent our test in our study of sciences. All right. So magnetic field, a set of imaginary lines that indicate the direction in which a small compass needle would point if it were placed near a magnet. These lines are indications of the magnetic force. Magnetic force field. That's kind of cool. It sounds like a Star Trek thing. Magnetic force field, right? Magnetic fields are vector quantities. Okay. So that's just a bunch of definition stuff, right? But I really want to just show you a picture of a magnetic field. So this is a picture of a magnetic field, right? And the interesting thing about this is that, um, well, the one cool thing is that if you had a whole bunch of iron filings and you just like dumped them on top of a magnet, they would actually form lines. The iron filings would form lines that look just like this. I wish I had a picture of that. Um, but that's okay. This is good enough. So the thing I want you to notice that is we have this big magnet here, right? And then um, if we bring a compass near it, right, depending on where you are, in relationship to the magnet, right? In relationship to the magnet, the compass will like make it look like you're kind of going around the magnet. You see what I'm saying here, right? This side is attracted to the north side right here, so it's red over there, blue over here, right? And then This one's actually on the other side right here, and it's attracted there to that one, and that one's attracted to that one, of course, right? And then when you're on the outer magnetic field lines, right? You're on the outer magnetic field lines. You can see how they kind of turn a little bit, right? They turn like that, right? Still having the south sides attracted to the north sides, and the north sides attracted to the south sides as they go on these lines. So the really interesting thing about this is that my mother-in-law, oh, by the way, my girlfriend's living with me again, thank God. Um, and so I think she was forced to live with me again because my mother-in-law had her house renovated last week, so they didn't have any place to go, and so that's why they came back. But while we were there back, while she was back at my house, we made amends. She doesn't want to throw me off the roof anymore, so thank God for that. But the point is, we were starting. Well, I've already watched everything there is to watch about Stranger Things, the show on Netflix. But she hadn't yet. My mother-in-law hadn't watched it yet, right? And there's this one part where Dustin is looking for the gate, right? And freaking 11 is screwing with all the magnetic fields around it to try to make Dustin go the wrong way. But before she does that, right, their science teacher was talking about how there's a huge magnetic field that's causing this gate to be open, right? You could use a magnet, and if you go around and circle the magnet, right, you'd actually see the magnet's needle point in a circular direction, indicating that the center of the circle would be where the gate was, right? And he's actually true. It turns out that that science teacher is a pretty good science teacher. I wish he was my science teacher when I was in high school. I probably would have not been such a bad kid back then. Whew, that was a bad time. Anyway, and so and so those the gate emits this huge magnetic field, and it's in circles, right? It's all in circles, and so Dustin with his magnet going around the field, you could he's pretty good with magnet, and he could see that it was starting to turn, and he would follow the turn around, right? And it kept on going in the same direction until 11 messed it all up, right? But it was working at the beginning there, and and that kind of phenomenon is absolutely true, and that kind of phenomenon is not just in the way that he said it too is very true. It's not just because there's a magnetic field, but also if there's an electric field, a huge power field would actually do it as well. Electric field would do it as well, right? So that's pretty cool. What's less cool is those kids have no idea how to use a freaking compass, like the like like his friends don't know how to use a compass at all. Um, let's see here. Everybody knows what I'm talking about, right? When I'm talking about Stranger Things, what they did in that show, right? Yeah. I mean, I know that was like the first season. It was like 4 years ago, 5 years ago, or something like that. But it was a very good demonstration of how magnets work. All right. So, sources of magnetism, right? The source of magnetism is moving and spinning electrons, right? Which is actually kind of funny because electricity is also what? The movement of electrons, right? That's why they're so intimately involved, right? Electromagnetism or electricity and magnetism, they're intertwined in this very intimate dance, right? Very intertwined, very happy with each other most of the time, right? So this Danish guy named Orsted, right, first discovered that a compass needle was deflected by a carrying wire, a current carrying wire, right? And that's what I was talking about a second ago, where it said like an electric field would actually affect the compass needle as well. When you had an open current, right, it deflected the compass needle. When you had a closed current, no deflection of the compass needle. Excuse me. A current carrying wire produces a magnetic field, right? So the stronger the current, the stronger the field. And then so from that, we can get this cool thing called an electromagnet that can be turned on and off. And I know you've seen an electromagnet before. Quite literally, it's a battery with wires attached to it, right? From the north side to the positive side to the negative side. And then you wrap the middle part of the wire in a nail, right? And then you can use it to actually pick up things and make it. It's not a very strong magnet, but it's still a magnet nonetheless. Okay. So, what kind of things can be made? What kind of things can you use to make magnets, right? Well, really, most materials have electrons going all kinds of random directions, and therefore the magnetic effect is canceled, right? It cancels each other out, makes them non-magnetic, because all their electrons are going, all over, all kinds of different directions. But there are a few materials that are known as ferromagnetic materials, right? And they have all of their electrons aligned, okay? And so these are iron, nickel, and cobalt. So those are the three metals that you can turn into magnets: iron, nickel, and cobalt, okay? In which many atoms combine to create magnetic domains, local regions of magnetic alignment with a single piece of iron, right? So a piece of iron with randomly oriented magnetic domains is not magnetic, but you could make it magnetic by just putting it inside a magnetic field, right? Putting it inside a magnetic field. So yes. So have you ever done this thing too, where you can get a magnet and you can get a needle and stroke as like a steel needle on the magnet, and then it'll turn the needle magnetic, and then if you put it onto like a bottle cap and let it float in water, it'll act like a compass, right? That's pretty cool, right? The next time you're stuck in the next time you're stuck in the wilderness, like on Naked and Afraid or something, and you need a compass to know where you're going, make sure the things you bring, because I think you're allowed to bring one thing with you when you go to Naked and Afraid, right? So you should contact your partner if you know who they are, right, and have them bring the needle, and you bring the bottle cap. Oh dang it, we still need a magnet. Well, that's a bad idea. Forget about that. So forget about that whole thing. Just, you know what? If you're stuck out in the middle of nowhere, just make sure you have a magnet and you have a needle and a bottle cap and some water with you, and you'll be fine. You'll be able to find your way back, right, to some highway, or end up in Florida or something like that. That actually happened to me once. I was driving back from Atlanta, Georgia, and I missed the highway because I thought I was going west, but in fact I was going south. But I was navigating by the sun. But when the sun gets to the middle of the sky, it's very difficult to know where the sun's going. So I was like, "Oh, this is definitely west, right? It's definitely west." We drive like 2 hours, and it's like the Florida Georgia line. I'm like, "Oh crap, I'm already in Florida. How'd that happen?" So it's a good time. Isn't that the name of a song? Florida Georgia Line? No, it's a band. It's a band. That's right. It's a band. Anyway, so you can definitely take a piece of metal and turn it into a magnet. That's if it's made of iron, nickel, or cobalt, right? So here's your next question: which of the following materials cannot be used to make a magnet? Turns out that band is named after a real thing, the Florida Georgia line. That's real. You can pass over that. You can drive over that thing. I've done it before, accidentally. Oh, that's not good. All right, 23 people have signed in and answered the question. The vast majority of you got that. I'm just going to have to resign myself to the fact that there will always be one or two people that get it wrong on purpose. All right, I just have to accept it. Okay, I just have to accept it. Uh, but yes, the only one that you cannot change into a magnet is aluminum. Aluminum cannot be changed into a magnet. Okay, or in the words of the British, aluminium. Aluminium. Okay, so let's just talk about what it looks like when you magnetize something. Okay, here's a piece of unmagnetized material. Let's say it's just iron that's not magnetized yet, right? And it's got all its electrons just all kind of in all kinds of random different directions. Okay, but then you pass a current through it, or you bring it near a magnetic material, right? And now all the electrons line up, right? All the poles line up, and that's how you make something magnetized, right? That's pretty cool. And so this is the same thing I was talking about, where you take a needle and you stroke it on a magnet. It does the exact same thing, because in the needle, right? In the needle, it's like all random, and then you stroke it on a magnet, and then it becomes ordered that way, and then you can use it as a compass needle. The magnetic domains are generally random. When the iron is placed in the magnetic field, the domain lines line up, usually temporarily. Interesting, interesting. Okay, we're going to have a couple more slides here and we'll end this so I can talk to the Monday group about their experiments. Electromagnets. Okay, I was just talking about this a second ago. That's crazy. It's like I knew what was here before I got here. Hey. A simple electromagnet consists of an insulated copper coil of wire wrapped around a piece of iron. So here's your insulated copper wire, right? Wrapped around a piece of iron, right? And then there's a switch there, which somebody told me like a couple weeks ago that the symbol for switch is two dots, and I didn't believe them. Turns out they're right. So good on you. Okay. And so the stronger the current, the stronger the magnet, right? That's probably why my electromagnets suck so much. They're always like, double A batteries. Maybe I should use one of these. What looks like a deer stand battery, like one of those deer feeding batteries that that they use there, right? So electromagnets are made of a type of iron that's quickly magnetized, and that magnetized, it's termed soft, right? And so you have here your battery, you attach it to, I don't know why you need a switch, but you could have a switch, wrap it around the metal, the soft iron, right? And then it will become magnetic, which is actually very interesting because if you take that out, since it's soft iron, and you take that out and it's no longer inside this electric field, it won't be magnetic anymore, right? So that's what it means when you're soft iron. It means that as soon as you leave the magnetic field, you're no longer magnetic. Okay. So this is usually when you do this as an experiment, it's usually like a nail, right? It's usually like a nail. So nails are not magnetic. You can wrap a wire around them and they become magnetic, right? But you take that wire out of them, right? Out of take the wire off of it, it's no longer magnetic. But if you nail it into the wall and you put a magnet on top of it, a magnet is attracted to it. Does that make sense? Right? So the nail itself won't pick up any iron filings or pick up anything on its own, but it's still attracted to a magnet, right? And that's actually an easy way, by the way, of figuring out where the studs are on your. Have you ever tried to hang up stuff on your wall and you're like, "Where's the stud at?" And then most people try to use a stud finder, right? What I do is I actually take a magnet and I kind of run it against the wall, and then whenever the magnet stops, that's where a nail is, and then up and down that wall where that magnet is where there's a stud because there's a nail there, right? It's way faster, way easier. You didn't know that, did you? That's a hack right there. It's a life hack. Yes, yes. Not only do you learn science here, you learn life hacks here. Okay, so the last thing I want to talk about is called the Curie temperature, right? And permanent magnets. So they're the materials that are ferromagnetic, like the iron, cobalt, and nickel, right? At very high temperatures, right, called the Curie temperature, lose their magnetism, right? They lose their magnetism. So for iron, right? For iron, 707 degrees Celsius is iron's Curie temperature. At that point, at that point, iron can no longer be magnetic because we've reached its Curie temperature, right? It ceased to be ferromagnetic, right? Permanent magnets are made by permanently aligning any magnetic domains with a piece of material. The one way to create a permanent magnet is to heat the ferromagnetic material above the Curie temperature and then cool the material under the influence of a strong magnetic field. Well, that's cool, right? So heat up the iron, right? And then bring a really strong magnet close by and then let it cool. And when it cools the metal down, it will be permanently magnetic. I actually didn't know that. That's pretty cool. I'm going to try that. I mean, I don't know how I'm going to get to 707 degrees Celsius, but that's, what my old boss used to say. I can only handle one catastrophe at a time, right? Well, he used to say two things. He used to say, I can only handle one catastrophe at a time. And he also used to say, if it weren't for the last moment, nothing would get done. So I live by both those rules. I have a couple more too. So the last question for today is this question here. Okay? The last question for today is this question here. The temperature at which materials lose their magnetic properties is known as absolute zero, which we actually talked about before, but it's not this. Oh, dang it, I just gave you an answer. The Curie temperature, the triple point, or the none of the above? None of the above. And let's see how everybody's doing real quick. Did someone really pick absolute zero? I literally said this is not the answer. That's fine. It's fine. Like I said, I have to resign myself to the fact that some people are just going to answer wrong on purpose.